All right, recording looks good. Let's go get started with this Math 221 exam. So, question 1, evaluate the limit if it exists. If the limit does not exist, state whether it's infinity, minus infinity, or neither. Justify your answer. If you use a theorem, like the squeeze theorem or L'Hopital's, clearly state which theorem you're using and why it applies. So, part A, we have the limit as x approaches infinity of the square root of 9x squared plus 6 over 2x plus 5. All right, so for questions like this, these can be a little bit tricky because you have this kind of weird radical on the top and this fraction on the bottom, obviously. But the way that you're going to want to do this is because you notice that, well, x squared, if you take the square root of that, that's x over x as well. We can actually kind of cancel these out nicely. Or not cancel, I guess, per se, but you'll see what I mean. So if we take this fraction right here, we say 9x squared plus 6 all over 2x plus 5, and we multiply both above and below by 1 over x, this is actually going to cancel really nicely. So what's going to happen is this 1 over x is going to go inside this radical, and it's going to turn into 1 over x squared times 9x squared plus 6. This is all going to be over, this should be a times, make sure it doesn't look like a minus, 1 over x times 2x plus 5. Simplifying just a little bit, we're going to get this is equal to the square root of 9x squared times 1 over x squared. It's just going to be 9. This is second term, it's going to be 6 over x squared. All of this is going to be over 2x divided by x is just going to be 2 plus 5 over x. Because these are all equal, we can rewrite our limit now as being equivalent to the limit as x approaches infinity of the square root of 9 plus 6 over x squared all over 2 plus 5 over x. Awesome. And now all you have to do is put infinity in. So we get this is equal to the square root of 9 plus 6 over infinity over 2 plus 5 over infinity. And right, when we divide something by infinity, that's going to go to 0, goes to 0. This is just going to be square root of 9 over 2, which is just 3 over 2. That's going to be our first answer. Awesome. All right, moving on to part B, we have the limit as x approaches 0 of e to the 3x minus 3x minus 1 over cosine 2x minus 1. So first thing we want to do for limits like these is just plug in the value. So this is going to give us e to the 0 minus 0 minus 1 over, this is going to be cosine 0 minus 1. This e to the 0 just turns into 1 minus 1 over cosine of 0 is 1 minus 1. This gives us 0 over 0. This is going to be one of our indeterminate forms. Not exactly sure how to spell that, which means we can use L'Hopital's. Just write it out. I can spell this one. All right. So by L'Hopital's, I'll just write it up here real quick. If we have the limit of f of x over g of x, say, and this is equal to one of our indeterminate forms like 0 over 0 or infinity over infinity, we can rewrite it as the limit of f prime of x over g prime of x. And these two things will be equivalent. Not equivalent to the 0, but equivalent to the limit, right? So let's go ahead and take these these derivatives, sorry. So equivalent by L'Hopital's, this is the same as the limit as x approaches 0 of the derivative of e to the 3x. It's just going to be 3e to the 3x. The derivative of 3x is just 3, so we subtract that, right? And now for the bottom, this cosine 2x, you could do this on scratch paper if you want to chain rule it, but you might be able to see the cosine is going to turn into a minus sign, 2x, and then multiplying that by the chain, which is just going to be the derivative of 2x, which is 2. And then this 1 goes to 0, right? The derivative of a constant is 0. So let's rewrite this as the limit actually, we can just plug it in. We don't need to make it look pretty. So let's plug in 0. We'll get 3e to the 0 minus 3 all over. I will move this 2 to the other side so it looks a bit prettier. You don't have to, obviously, of sine 0, right? Because the 0 is going to cancel that too. This is just going to be equal to 3 minus 3 all over 0, which is 0 over 0. And this is, again, an indeterminate form, which means we can use L'Hopital's. Not sure why computer's freaking out up there. All right, so again, let's use L'Hopital's. So this is going to be equivalent to the limit as x approaches 0 of the derivative of e to the 3x is again going to be 3e to the 3x. So if we just factor out this 3, right, we can do the exact same derivative. Hopefully that makes sense. And then on the bottom, we'll factor out this minus 2, right? And now the derivative of, I'm just looking at this part right here, the derivative of sine of 2x, well, that's going to be cosine of 2x times the chain, which is going to just be 2, right? The derivative of 2x is 2. So I will simplify this one just a little bit. This is the limit as x approaches 0 of 9e to the 3x over, that's going to be what, minus 4 cosine 2x. Plugging in 0, we get 9e to the 0 over minus 4 cosine 0. E to the 0 is 1, so we just get 9 on the top. Cosine 0 is 1, so we just get minus 4 on the bottom. And actually, I'll just write out this last step, putting the minus up here. You definitely don't need to do this, but it looks prettier. All right, perfect. Moving on to part C now. Oh, there goes my pen. We have the limit as x approaches 0 of e to the x minus 1 all over tan x. First thing, let's go ahead and plug in 0, see what happens. So we're going to get e to the 0 minus 1 over tan 0. E to the 0 is just 1, so this is 1 minus 1 up on the top. And on the bottom, tangent of 0 is going to be 0, but just in case, if you want to write it out explicitly, right, we have sine 0 over cosine 0. The sine 0 is just going to be 0, cosine 0 is 1, so that's how we know, right, because tangent is sine over cosine. In case you forget, because I've definitely done that on a test, so this is just going to be 0. Thus we get 0 over 0, which is, again, one of our indeterminate forms, which means we can use L'Hopital's. Perfect. All right. So by L'Hopital's, we get that this is equivalent to the limit as x approaches 0 of the derivative of e to the x is just e to the x. The derivative of 1 is just 0, right? And now the derivative of tangent, this one's a little bit trickier, but hopefully you remember that's going to be secant squared x. If you forget on the test, worst case scenario, you could absolutely differentiate sine x over x using a quotient rule. I wouldn't recommend it. Try to remember that derivative, but yeah, you could absolutely do something like that if you forgot. All right, and now what we can do is we can rewrite this as the limit as x approaches 0. What is secant x? Well, that's just 1 over cosine x, so we can actually bring that to the top as cosine squared x times e to the x. I'll put parentheses around that so that's clear. And now let's go ahead and plug in 0. This is going to be cosine squared of 0 times e to the 0. Cosine of 0 is just 1. Square that, it's still just going to be 1. E to the 0 is just 1. So this all goes to 1, just like that. And that is going to be the end of question 1. All right, moving on to question 2. Compute the following derivatives. Use any method. You do not need to simplify your answer. So part A, we have that f of x is equal to sine x square root x plus 3, or times the square root of x plus 3, I suppose. So this one is going to be product rule, which we can tell because, right, this is sine x times the square root of x plus 3, so we're definitely going to need product rule. I'll just work out the two derivatives on the side real quick. The derivative of sine x is just cosine x, and the derivative of the square root x plus 3. Well, we can rewrite this as the derivative of x plus 3 to the 1/2. And so now we can just use power rule, right? Bring the power down. This is 1/2 times x plus 3 to the minus 1/2. And of course we are implicitly using the chain rule here, but the derivative of x plus 3 is just 1, so it doesn't really matter, right? Times 1, same thing as just ignoring it. All right, so now we can rewrite this all. So we have f prime of x is equal to the derivative of the first, which is going to be our cosine of x term, times the second, which is just square root x plus 3, plus the derivative of the second, which is going to be 1/2 times x plus 3 to the minus 1/2 times the first, which is just sine of x. And yeah, that's going to be about it. We don't need to simplify, so we're all good. All right, moving on to part B, we have that g of x is equal to natural log of x squared plus 1 over 2x plus 6. For this, we have a quotient, so we're going to be using the quotient rule. This one's a little bit more complicated, so I'll go ahead and write it out over here. Just remember the quotient rule is, say we're taking the derivative of, I'll use f and h, so f of x over h of x. That is going to be equal to the bottom times the derivative of the top minus the top times the derivative of the bottom, all over that bottom term squared, just like that. So now let's go ahead and calculate these derivatives separately as well. So we have the derivative of, it's going to be this natural log term. I'll go ahead and write out the derivative of natural log with u, just in case you forgot. So remember the derivative of, let's say ln u, this is going to be 1 over u times u prime, right? Just chain ruling it. So if we take, I'll stay in orange, I suppose, the derivative with respect to x of natural log x squared plus 1, this is going to be 1 over x squared plus 1 times 2x, right? The derivative of x squared is 2x. And also, we can write it out for thoroughness. The derivative of 2x plus 6, that's just going to be some basic power rule. That's just going to be 2, right? So now we can find g prime. So I'll give myself some space. G prime of x, this is going to be equal to the bottom, 2x plus 6, times the derivative of the top, which we found to be 2x over x squared plus 1, minus the top, which is natural log x squared plus 1, times the derivative of the bottom, which is just 2. All of this over, there we go, the bottom term squared, 2x plus 6 squared. Again, we don't need to simplify, so I wouldn't even bother rearranging it all. All right, part C, we have h of t is equal to e to the cosine t. All right, so this is going to be chain rule. Again, right, because we have kind of two functions embedded in one another. So let's say, just recall the derivative with respect to u of e to the u is just going to be u prime times e to the u, right? Just chain rule here. So now let's say u, that's going to be our cosine term, right? What is the derivative of cosine? Well, that's just going to be minus sine of t. Sorry, the derivative of cosine t is minus sine of t, to be clear. And actually with that, we can already calculate our answer. So h prime of t is just going to be equal to e to the cosine t times, what is u prime in this case? Well, that's minus sine of t. And minus sine t. And yeah, that's it. I wouldn't even bother rearranging again. You could always drop a negative. Done that plenty of times. So that's going to be our answer. All right. Moving on to question 3. Compute the following integrals. Use any method from this course. You do not need to simplify your answer. So for this one, I'm going to write I equals just to keep track. You definitely don't really need to do this. We have the integral of secant squared t plus cosine t plus 1 over 1 plus t squared. All right, so this problem is really testing two things. One, you really need to remember for this one that you can split integrals on like addition, subtraction. They're linear, in other words. So this is actually going to be equal to the integral of secant squared t dt plus the integral of cosine t dt plus the integral of 1 over 1 plus t squared dt. And the second thing this problem is testing is if you remember those integral rules, sorry. So I'll write the equals over here so it's clear. The integral of secant squared t, that's going to be tangent t. The integral of cosine is just sine t, not minus sine t, had to think for a second. And the integral of 1 over 1 plus t squared, this one's a little bit trickier. This is going to be our inverse tangent, or arctangent, however you want to call it, of t. And then do not forget your plus c. And yep, that's going to be it. All right, I'll put a little note. This is also equivalent to arctan. Same thing. Okay, so next up for part B, we have the integral of x cubed over square root x squared plus 5 dx. And so for this one, because we kind of have a weird radical here on the bottom, we have a pretty good idea that we're going to want to use u sub. And generally with u sub, you want to get rid of ugly radicals. So we'll let u be equal to x squared plus 5. This means that du is going to be equal to 2x dx. And we're going to need one more piece because we see we have an x cubed on the top, and we only have an x for the that we're going to cancel with the du to dx transition. So we're also going to want to get that x squared is equal to u minus 5. Right? I'm just moving this 5 to the other side. So we can rewrite our integral now as the integral. Let's get this 2x term. So we're going to have to multiply by a 1/2 in the front, so it cancels with a 2. And then I'm going to split this x cubed into an x for the 2, and also a times x squared term right here, all over the square root of x squared plus 5 dx, right? And now I'm going to plug in my u's, so this is equal to 1/2 times the integral of this 2x and the dx turn into du, right? So we can ignore it for just a second. This x squared turns into u minus 5, and the bottom turns into the square root of u. And remember, we get the du from the 2x dx right here. Perfect. Okay, so now let's go ahead and simplify this just a little bit. We can rewrite this as 1/2 times the integral. I'm going to bring this 1 over square root u up by writing it as u minus 5 times, it's going to be u to the minus 1/2, right? Du. Let's go ahead and distribute that just a bit. We're going to get this is equal to 1/2 times the integral of u times u to the minus 1/2. Remember, we add the exponents when we multiply like bases, right? So this is just 1 minus 1/2, which is u to the 1/2. Hopefully that makes sense. And then we're going to subtract 5u to the minus 1/2, just like that, du. And now we can finally integrate. So this is going to be 1/2 times the integral of u to the 1/2. This is just going to be power rule. So add 1 is 3 over 2, multiplied by the reciprocal is 2 over 3. So 2/3 u to the 3 over 2 minus 5, and I'll factor that out so we can do it a bit easier. 1 plus minus 1/2 is going to be 1/2, multiplied by the reciprocal of that is 2. So 2u to the 1/2, just like that. And this is an indefinite integral, so we don't have any bounds. We can just add our plus c way out here. All right, and we have this is equal to. Let's bring this half through, just like this. It's going to cancel with this 2 right here, so we get 1/3 u to the 3 over 2 minus this 2 is going to cancel with this 2 right here. So we get minus 5u to the 1/2, and then we add our c, just like that. And now remember, don't forget to plug back in our u from up here. So this is just going to be equal to 1/3 times x squared plus 5 to the 3 over 2 minus 5 times x squared plus 5 to the 1/2 plus c, and that's going to be our final answer right there. Awesome. All right, moving on to part C now. Here, this looks really ugly at first, but if you notice, we're going to be able to do a nice u-sub. So this is going to be the integral from 0 to pi over 2, so we're doing a definite integral this time, of sine to the 7th x cosine of x. And as I just said, this is going to be a u-sub. And the way we can tell here is, well, we have sine and cosine, which we know the derivative of sine is cosine. And since we have just one cosine here and a lot of sines, that's going to be a really good indicator that we can get rid of this cosine by letting u be equal to sine of x. And as you'll see, this will also make our sine terms a lot nicer. So if we differentiate, we get du is equal to cosine x. This is what I was trying to say, right? This du is going to get rid of the cosines, and then all of our sines group nicely with u. And the other thing we have to do is we're going to want to change our bounds. So you could leave your bounds as 0 and pi over 2, but then you would have to convert back to x's at the very end. And just so I don't get confused, I'm going to swap my bounds now. So if I have x is equal to, I'll do the top bound first, pi over 2, well, this tells me that u is equal to sine of pi over 2, and sine of pi over 2 is 1. I had to think about the unit circle for a second there. All right, and then if we have x equal to 0, this gives me that u is equal to sine of 0, which is just 0, right? Because sine goes through the origin. All right, so now we have that I is equal to the integral from 0 to 1 of sine to the 7th x. Well, that's just going to be u to the 7th now, right? And cosine x dx, well, that's just going to be du. And we can already integrate. This is going to be u plus 1 is, 7 plus 1 is 8. The reciprocal of that is 1/8, u to the 8th from 0 to 1, right? And this is going to be pretty easy, right? We just get 1/8 times 1 minus 1/8 times 0, and hopefully you can see this is just 1/8. Awesome. All right, nice and easy. Moving on to this last one, part D. This one's going to be a decent bit trickier. So we have the integral from 1 to 4 of the absolute value of x minus 3 dx. So the way I like to approach these problems is by splitting my absolute value into a piecewise function. If you don't remember that, don't worry, that's just where we look at kind of two different cases. So what I can say is x minus 3, well, that's going to be equal to two different things. Half the time, it's just going to be the exact same as x minus 3 whenever x is greater than or equal to 3, right? If I plug in a 4 to this absolute value, the absolute value bars don't do anything. But if I take any value less than x is equal to 3, say I plug in 2, well, that's 2 minus 3, that's minus 1, and then I have to negate it. So all that this is saying is when x is bigger than 3, absolute value bars don't do anything. When x is less than 3, they negate it. And so what I can do now is I can split up my integral. So I can say that it's the integral from 1 to 3, right, because that's where x is swapping, of, this is the minus, pretty bad voice crack, this is the minus portion, minus x minus 3 dx, and then we're going to add to that the integral from 3 to 4 of x minus 3. This is the positive portion, greater than 3. And here, let's go ahead and distribute that negative before we integrate. This is the integral from 1 to 3 of minus x plus 3 dx plus the integral from 3 to 4 of x minus 3 dx, just like that. And yep, those negatives look about right. Let's go ahead and integrate. This is going to be equal to the integral of minus x is going to be minus 1/2, put some brackets around this, minus 1/2 x squared, plus the integral of 3 is just going to be 3x. We're going from 1 to 3. And then we're going to add to that second integral. This one, the integral of x is 1/2 x squared. The integral of minus 3 is minus 3x. And this one goes from 3 to 4, just like that. All right, and let's go ahead and start doing some arithmetic. This first one is going to be minus 1/2 times 3 squared is going to be 9. I'll simplify that much for him. Plus, that is not what I want to write. This is going to be 3 times 3. And then we have to, I'll put some parentheses around this, subtract from this, minus 1/2. We're multiplying by 1 now, plus 3, just like that. And then we're adding to this 4 section, this is going to be 1/2 times 16, right? 4 squared is 16, minus 3 times 4. And we subtract the 3 portion, 1/2, 9, I'll simplify that, minus 3 times 3, just like that. All right, at this point, if this was my test, I would box this answer right here. Sorry, I got a quick sip of water. But just because there's a couple different ways you could do this, you could do this geometrically as a little hint. I'll go ahead and simplify this just a bit. This is going to be minus 9 over 2 plus 9. This is going to be plus 1/2 minus 3 plus 8 minus 12 minus 9/2 plus 9, just like that. And you can see why I would not want to do this on a test. Let's go ahead and combine this 9/2 and this 9/2, which is going to give me a minus 9. And then there's a plus 9 right after that. This 1/2 is going to stay, I think. And then we have minus 12 minus 3 is minus 15. And then we have plus 8 plus 9 is going to be plus 17. So these two 9s cancel. This is going to be equal to 17 minus 15 is 2 plus 1/2. That is going to be 5/2. So that is the simplified answer. Of course, again, I would highly recommend you just leave it as this on your test up here. All right. Moving on to question 4. We have a plane is flying horizontally at an altitude of 1 mile and a speed of 500 miles per hour. Oh, I read that wrong. A plane flying horizontally, there we go, at an altitude of 1 mile and a speed of 500 miles per hour passes directly over a person. Find the rate at which the straight line distance from the plane to the person is increasing when the plane's straight line distance from the person is 2 miles. So this is one of those ones where I think it's going to help to draw a picture. So let's say this is the person right here, and obviously they're standing on the ground. So the plane is flying over at a height of 1 mile, right? 1 mile right here. And so what we're saying, the plane passes the person, so it goes this way. I'll say it's going this way, I suppose. And it ends up where it is 2 miles from the person. This probably isn't to scale, but you get the idea. And so what we want to find is how much this distance, I'll do it in orange, this distance right here is increasing. So the way we're going to do this is with the Pythagorean theorem, actually. So let's call this distance z. Let's call this distance y, which is equal to 1. Let's call this distance x. So we know, thanks to Pythagoras, that z squared is x squared plus y squared. And we also know that y is just equal to 1, so y squared is also equal to 1. So this is just x squared plus 1. So we get that z squared is equal to x squared plus 1, just like that. And so now what we want to do is use some implicit differentiation, because we're looking at it with respect to time. So what you can say is we're going to differentiate this side with respect to t. So derivative with respect to t of z squared is equal to the derivative with respect to t of x squared plus 1. Right. And so hopefully you remember how implicit differentiation works, but all it's going to be, we're going to take the derivative of z squared, which is 2z, and then we also have to multiply it by the chain of this, which is dz dt. Nothing too crazy, right? And the derivative of x squared is going to be the exact same. We get 2x times dx dt. Just like that. The derivative of 1 is just going to be 0, so we don't have to worry about it. And what we're interested in here is how this straight line distance is increasing, right? Which is going to be our dz dt term right here. So we'll go ahead and bring this 2z over, because we don't really care too much about it. we get dz over dt is equal to, the 2's are going to cancel, and we get x over z times dx over dt, just like this. And this is where you're going to really have to read that given information. We know that, let's see, z is going to be 2, right, because the distance is 2 miles, which it says right here. So I'll start writing our information here. Z is equal to 2. We also have that the speed of the airplane is 500 miles per hour. And so that's going to be the change in x up here. So we know that dx dt is equal to 500. And the last thing we have to find is x. And so we can actually use that using the Pythagorean theorem we have up here. So we have that z squared is equal to x squared plus 1. And we want to find x squared. So we'll say x squared is equal to z squared minus 1, or x is equal to plus or minus the square root of z squared minus 1. And so now let's plug in z. We know z is 2. So we get x is equal to plus or minus the square root of 2 squared is 4. So 4 minus 1, that's going to be 3. We get x is equal to plus or minus square root of 3. Doesn't need to be that big. All right. And so for now, we are going to be looking at this positive side over here, right? We said the plane passed over the person. So we are only looking at the x is equal to positive square root 3. So that's all of the information we need. We can start plugging it in. We get that dz dt is equal to x is square root 3 over z is 2 times dx dt, which is 500. And this is going to be 500 over 2 is 250. So we just get 250 times the square root 3. And do we need units? It doesn't say. Let's go ahead and include them. Just looking at this real quick, we know that x is in units of feet. Z is in units of miles. So miles over miles, that's going to cancel. So we're just going to keep the units of the dx dt, which is in miles per hour. You could also probably figure that out because it's a rate. All right, that's our final answer. Moving on to question 5. We need to find all the vertical, horizontal, and or slant asymptotes of the given functions. So for this first one, we have that f of x is equal to 2x squared plus 3x minus 1 over 2x plus 1. All right, so just to quickly remind you, for vertical asymptotes, those are going to be the easiest ones to spot. Vertical asymptotes happen when the bottom portion, so I'll call it the denominator, that's what I was looking for, denominator is equal to 0, and it doesn't cancel, right? And so next up, horizontal asymptotes. That's going to happen when the degree, which is the highest power up here, so the degree of the top would be 2, because that's the highest power. The degree of the numerator, I'll just shorten it to numerator, num, is equal to the degree of the denominator, I call it den. And lastly, we have slant asymptotes. Those are going to occur when the degree of the numerator is equal to the degree of the denominator plus 1. So we can see we're probably going to have a slant asymptote. We'll have to check for that. But the first one is we're going to want to check for a vertical asymptote when the denominator is equal to 0. So let's go ahead and take a look. When does 2x, not plus 1, 2x plus 1 is equal to 0? Well, we can rearrange. I'll do it fully. We get 2x is equal to minus 1, which gives us x is equal to minus 1/2. And we just have to check, make sure that this top portion isn't also equal to 0, because then you'd be able to cancel it, right? So let's just go ahead and take a quick peek. We have 2 times minus 1/2 squared is going to be 1/4, plus, actually I'll put parentheses around the full thing, plus a 3 times minus 1/2 minus 1 this is going to be equal to 2 over 4 is 1/2 minus 3 over 2 minus 1. And we can already see here 1/2 minus 3 over 2, that's going to be negative. If we keep subtracting, this is definitely not going to be equal to 0. So I'll go ahead and start writing my answer down here. We know we're going to have a vertical asymptote at x equals minus 1/2. All right, next up, to check for horizontal asymptotes, I have it over here. We want to see is the degree of the numerator, which is 2, the same as the degree of the denominator, which is an implied 1. No, so we're not going to have any horizontal. For slant, is the degree of the numerator 1 bigger than the denominator? And in this case, it is, right? Because 2 is 1 greater than 1. So the way we're going to check for a slant asymptote is by taking this denominator and then dividing the numerator by that. And we're going to do that with the long division. So we're going to have 2x plus 1 divides 2x squared plus 3x minus 1. And this is one of those things that I feel like I always forget how to do, but we're just going to put an x here. X times 2x plus 1, that's going to be 2x squared plus x. Subtracting, we get 2x minus 1, and we'll do one more. We're going to add 1 to this. 1 times 2x plus 1 is 2x plus 1, and we're going to get a remainder minus 2. We don't care too much about this remainder. All we're looking at here is this is going to be our slant asymptote right here. So we're going to have a slant asymptote of x plus 1. I suppose I should say y equals x plus 1. Y equals x plus 1. And I think that's all we need to do for this. Yep. Cutting into that in the next problem a bit. All right. So next problem, part B, we have g of x is equal to 2x cubed plus 4 over x cubed minus 2x squared minus 8x. So just remembering these rules from up here, right? We want to first check for vertical asymptotes with the denominator being equal to 0. So x cubed minus 2x squared minus 8x. Let's go ahead and factor this. I'll say it set equals 0 now. So factoring, first thing we can do, we can plot an x from all these, and we get x squared minus 2x minus 8. And next up, we can go ahead and factor this middle part as, I think it's going to be minus 4 and 2. Yep, because minus 4 plus 2 is minus 2, multiplied is minus 8. So we have x times x plus 2 times x minus 4. And double check, yep, that looks right. And this is equal to 0. So this is going to occur, I'll write it up here, when x is 0, x is minus 2, and x is 4. And we can quickly double check. None of these are going to divide the top because it's this this cubic, right? Because say we have the x minus 4 term, there's no way this is going to divide 2x cubed plus 4. Right, so we know we're going to have vertical asymptotes at all of those points. Next, we need to check for horizontal and slant. So first thing, check the degree. So that's the highest power, right? So we have a 3 and 3. Because that's equal, we know we're going to have a horizontal asymptote, no slant asymptotes. And the way that we check for horizontal asymptotes is we're going to take the limit as it goes to infinity. So the limit as x approaches infinity of 2x cubed plus 4 over x cubed minus 2x squared minus 8x. And the way we're going to do this is actually the trick we used on the very first problem, but I'll remind you in case you didn't see that one. What we're going to do is we're going to multiply both the top and the bottom by 1 over x cubed, which is the shared highest power. So say we have 2x cubed plus 4 over x cubed minus 2x squared minus 8x. We're going to multiply the top by 1 over x cubed and the bottom, sorry, not a fraction, I guess it is. Multiply this by 1 over x cubed as well. This is going to be equal to 2 plus 4 over x cubed all over x cubed is going to be 1 minus 2 over x minus 8 over x squared. Just like that. So now, as we can see, when we take the limit as x approaches infinity of 2 plus 4 over x cubed over 1 minus 2 over x minus 8 over x squared. Yep. We know that all of these terms are going to go 0. I'll write it out explicitly, though. So this is going to be 2 plus 4 over infinity over 1 minus 2 over infinity minus 8 over infinity. And this is going to go to 0, this is going to go to 0, this is going to go to 0. And the other thing I will note is if we had a minus infinity instead of just a normal infinity, none of these would change, right? All of these are going to 0, all of these are staying the same, it's just going to be equal to 2. So plus or minus infinity doesn't matter. So we're going to have our vertical asymptotes. I'm just writing out the final answer. Vertical asymptotes are at x is equal to, it was minus 2, right? Yep, x is minus 2, 0, and 4. We're going to have a horizontal asymptote at x, no, this is going to be at y is equal to, right? These horizontal asymptotes we determine by y values. So this is going to be at y is equal to 2. I'll just put in parentheses both directions, right? Because it's in the positive infinity direction and the negative infinity direction. Awesome. All right, that is question 5 done. All right, moving on to question 6. Use the limit definition of the derivative to find f prime of 2. No credit will be given if you do not use the limit definition. All right, this one's going to be ugly. So we have f of x is equal to 1 over square root of x minus 1. All right, and just remember, I'll write it up here. The limit definition of the derivative is just that, f prime of x is equal to the limit as delta x, or sometimes you'll see this as h, approaches 0 of f of x plus delta x minus f of x over delta x. And yeah, this is the limit definition. So what we're going to want to do is start cranking out some calculations. So we have f prime of x is going to be equal to the limit as delta x approaches 0 of, I think I'm going to plug these in right away because we're going to need the space, f of x plus delta x, that's going to be 1 over the square root x plus delta x minus 1. And then we're going to subtract from this 1 over just f of x, which is square root of x minus 1, all of this over delta x. And so for this first step, what I'm going to do is I'm going to rewrite this as the limit as delta x approaches 0. I'm going to pull this 1 over delta x to the front so I can multiply a little bit nicer. And I think I'm going to need the space. So what I'm going to do is I'm also going to multiply this first one by square root of x minus 1 over square root of x minus 1. So here, I'll write it up here. I have the term 1 over square root x plus delta x minus 1. If I multiply both the top and the bottom by the square root of x minus 1, square root of x minus 1, this fraction is just 1, so it doesn't really matter. So I can rewrite this first one as square root of x minus 1 over, it's going to be square root of x plus delta x minus 1 times the square root of x minus 1. And I'm going to do the exact same thing for the other fraction, but instead multiply by the square root of x plus delta x minus 1. So this is going to give me minus, on the top, I'll get square root of x plus delta x minus 1 over square root of x plus delta x minus 1 times the square root of x minus 1, just like this. Double check all these signs because you do not want to make a mistake on this. All right, so now what I can do is I can combine these. So this is equal to the limit as delta x approaches 0 of 1 over delta x times, this is going to be square root of x minus 1 minus the square root of x plus delta x minus 1 all over square root of x plus delta x minus 1 times the square root of x minus 1, just like that. All right, and so right here, what I'm going to do to simplify is, it's one of those techniques that I feel like I always forget. It's going to be multiplying by the conjugate. And so all the conjugate is we're looking at this numerator right here. We have the square root of x minus 1 minus, the conjugate is just going to be switching this to a plus. And so actually I'll write it over here in orange. So we have the square root of x minus 1 minus, let's make it a little bit nicer, minus the square root of x plus delta x minus 1. And so the conjugate is, this is over some stuff, is going to be the square root of x minus 1 plus the square root of x plus delta x minus 1. All right, so when we do that, you'll see it actually simplifies very nicely. I'm running out of space here, but this is going to be equal to the square root x minus 1 times the square root x minus 1. That's just going to be x minus 1. And then we're going to have a minus square root x minus 1, square root x plus delta x minus 1 term. And then what you'll see here is now we're moving to this part. This positive term multiplied by this is actually going to cancel this other term. So we're going to get plus square root x minus 1, square root x plus delta x minus 1. Run out of space here. Go ahead and move it over just a bit. And when we add these other two, it's going to be this positive term times this negative. So it's going to be negative x plus delta x minus 1, just like that. This is all going to be over. It's going to be a very ugly term, but I suppose I'll do it here actually. This is going to be our square root x plus delta x minus 1 times the square root of x minus 1. And this fraction, sorry, I should have wrote this so it's a bit clearer. We're multiplying it by a fraction that's equal to 1, right? So this bottom term is, I'll leave it unexpanded for now, x plus delta x minus 1 times the square root of x minus 1 times the square root of x minus 1 plus the square root of x plus delta x minus 1. All right, so let's go ahead and I'm going to move some of this stuff around just so I have a bit more space. Unfortunately, you can't do this on your test, so sorry about that. We have that this original limit is going to be equal to the limit as delta x approaches 0. Actually, while I'm here, let's go ahead and simplify. So when we look over here, right, this term is going to cancel with this term. So we have that this is equal to the limit of 1 over delta x times, we have our x minus 1 term, minus, and I'm running out of space, so I'm going to distribute this minus to this x, this delta x, and this 1 right here. So we have minus x, minus delta x, minus times a minus 1, that's going to be a plus 1, just like this. And on the bottom, we have this very large term. So this is going to be square root x plus delta x minus 1 times the square root of x minus 1 times square root of x minus 1 plus the square root x plus delta x minus 1. And this is what I meant. This is a pretty ugly problem. We're going to move this over just a bit. And so what we see here on the top is that this x cancels, and these two 1s are going to cancel. So when we multiply this delta x in, it's going to cancel with this delta x. So we're just left with the limit as delta x approaches 0 of, it's going to be a minus 1 on the top, all over this big fraction here. So square root of x plus delta x minus 1 times the square root of x minus 1 times the square root of x minus 1 plus the square root of x plus delta x minus 1, just like that. All right, perfect. And lastly, we can now plug in this delta x as 0. So this is going to be minus 1 over the square root of x plus 0 minus 1 times the square root of x minus 1. Put that in parentheses. This is times the square root of x minus 1 plus square root of x minus 1. And I'm starting to run out of space here, so I'm going to have to move all of this up. Let's see here. Yeah, probably should have started a decent bit higher on this problem. All right, so I lost a minus 1 here. Where does that go? Up here. Minus 1. Okay, so now I'll go ahead and simplify here because we also still need to plug in 2. This is going to be minus 1 over this term, right? The 0, we can ignore it. This is x minus 1. This is going to be 2 times the square root of x minus 1. So I'll bring this 2 way out here. And then if we have x minus 1 to the 1 times x minus 1 to the 1/2, this is going to be x minus 1 to the 3 over 2, just like this. So that's going to be our final answer. And of course, you can always check for these limit definition problems if you want. We have x minus 1 to the minus 1/2. This is minus 1 over 2 times x minus 1 to the minus 3 over 2, which is exactly what we have down here. Last thing we need to do is calculate f prime of 2. So f prime of 2 is just plugging that in. So you get minus 1 over 2 times 2 minus 1 to the 3 over 2. This is minus 1 over 2 times 1 to the 3 over 2, which is just minus 1/2, which that one does thankfully simplify nicely. All right, so now the rest of this won't be too bad. All we need to do is find the equation of a tangent line when x is equal to 2. So to do this, we're going to want to find f of 2. So f of 2, this is 1 over the square root of 2 minus 1. This is 1 over the square root of 1, which is just 1, right? And so now we can write y minus y1 is 1. It's equal to the slope times x minus x1, which is 2. Sorry, I'll write out the formula. Right? Y minus y1 is equal to m times x minus x1. Just to be explicit, this should be a perfectly fine answer. I'll go ahead and put it in the y equals mx plus b form that you are probably more familiar with. This is y minus 1 is equal to minus 1/2 x plus 1. Yep. And we can move it to the other side. This is y is equal to minus 1/2 x plus 2, which is also a valid answer. These two lines are the exact same. All right, moving on to question 7. All right, this question's a little bit nicer, thankfully. So for question 7, we have that f of x is equal to the square root of x cubed plus 6x squared plus 4. And we want to find the maximum and minimum on the interval minus 2 to 2. Make sure to write your final answer listing both the x and y coordinates of the points. Okay, and we also have this little note that I'm sure will be helpful, that x cubed, or the term on the inside, is always greater than 0 when x is greater than minus 6. So we don't have to worry about any weird discontinuities. So to solve this, first I'm going to rewrite this square root as x cubed plus 6x squared plus 4 to the 1/2 power. And so now I can use some chain rule to find the derivative. So f prime of x is going to be equal to, I think we're going to need a little bit of space, so I'm not going to write the full chain rule. You could absolutely do this on scratch paper, but this is going to be bring the 1/2 power down, x cubed plus 6x squared, sorry, I lost a squared here, plus 4 to the minus 1/2, right, because we're subtracting. And then we're going to multiply by the derivative of the inside. That's going to be 3x squared plus 12x, just like that. And sorry, that 12's kind of ugly. And let's go ahead and write this as the full fraction. This is going to be 3x squared plus 12x over 2 times x cubed plus 6x squared plus 4 to the 1/2 power. Okay, so we're interested in finding the maximum and the minimum. Because we know that this term right here is positive, we don't have to worry about any weird asymptotes. So we want to find when this whole term is equal to 0, and that's actually only going to happen when the numerator is equal to 0, right? So f prime of x is equal to 0. Well, that's going to be equivalent to the numerator being equal to 0, because you can never divide by something and get 0. except the limit as we approach infinity, but thankfully we don't have to worry about that. So we're going to get 3x squared plus 12x is equal to 0. Let's go ahead and factor out a 3x. We get 3x times x plus 4 is equal to 0. And so we're going to get 2x values here. We know that this whole term is going to be equal to 0 when x is 0 or when x is equal to minus 4. And let's go ahead and look at our bounds real quick. We're from minus 2 to 2, so we actually can ignore this minus 4 term. Now what we want to do is figure out whether x equals 0 is a maximum or minimum or neither, I suppose. The way that I'm going to do that is with number line analysis. So I'm going to look at f prime, and I'm going to look at it around 0. So I have f prime of 0. And so what I want to see is what does f prime look like before 0, and what does it look like after 0. So I'll just plug in f prime of minus 1 and f prime of 1 and see what's happening. So f prime of minus 1, that is going to be 3 minus 12 over 2. And actually, I can do a little bit of a cheat here. Because I know this bottom term is always going to be positive, I can just actually write that this is going to be some positive number. This is going to be 3 minus 12. That's going to be a negative on top, positive on bottom. So I know that this is going to be a negative result right here because I'm just interested in the sign. I'm not interested in the actual value. All right, now with positive 1, this is going to be 3 plus 12 over 2 times some sort of positive, which is positive over positive, which is going to be a positive. So I know that f of 0 is going to be a minimum. Voice cracks, all right? All right, so now let's go ahead and look at these values. So I'm going to need to find f of 0, and then I also need to find the endpoints. So I'm going to need to find f of minus 2 and f of 2 as well. So f of 0 is going to be the square root of 0 plus 0 plus 4, which is just going to be 2. F of minus 2 is going to be minus 2 cubed, which is minus 8, plus 6 times minus 2 squared is 4, right? Plus 4. This is the square root of minus 8 plus 24 plus 4, which is going to be the square root of 20. And lastly, we have f of 2 is equal to the square root of 8 plus 6 times 4 plus 4, which is going to be equal to the square root of 8 plus 24 plus 4, which is the square root of 36, which is 6. And so we're looking for one maximum, one minimum. So we know the max is going to be at 36, the min is at 2. So I'll just write that here. Max is going to be at 0, 2. Min is at 2, 36. Perfect. All right, moving on to question 8. We have sketch a graph of a function f of x that has the following properties. So f of minus 3 is 0. Actually, before I read through these, let's go ahead and put some tick marks on our graph. So looks like interesting stuff happens around 4 and minus 3. So I'll go ahead and put 5 tick marks. So we'll say we have 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And last one, 1, 2. All right, perfect. So now let's just go one by one. F of minus 3 is going to be 0. So I'll put a point right here. And I'll put a little arrow so we know minus 3, 0. All right, we also have f of 0 is minus 4. So that's going to be down here. F of 0 is minus 4. And I think we have one more. Yep, f of 4 is going to be 3. So f of 4 is going to be 3. All right, now let's go ahead and look. So we have the limit as x approaches 1 from the negative side is going to be negative infinity, and the limit as x approaches 1 from the positive side is also negative infinity. And so what that tells us is we're going to have an asymptote. So at 1, we're going to have an asymptote, and we're going to negative infinity, so I'll just mark it up here. This line is x is equal to 1. I'll make my 1 look nice. And we're going to negative infinity, so we're gonna kind of swoop down here. Okay. Lastly, we have our derivatives and second derivatives. So just to make it a little bit clearer for myself, I'm going to write out some number lines. So f prime, let's see, where is it changing sign? So 0, 1, and 4, it looks like. No, I'm sorry, 1 and 4, actually. So we have 1 and 4. So from minus infinity to 1, we know it's going to be negative. And from 4 to infinity, it's also negative. And from 1 to 4, it's positive. All right, what about our second derivative? We know that it is going to be positive from minus infinity to minus 3. And it is going to be negative from minus 3 to 1 and from 1 to infinity, right? And we know there's that little discontinuity because of the asymptote. So we're going to have a decreasing function that is concave up in this little back portion, and then it's going to switch to concave down. So it's always decreasing up until this asymptote is what we're seeing, and it switches concavity. So what we can do is we can draw that like this. Going down, 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 down. Is the derivative equal to 0 at minus 3? Let's see. Nope, it is not. So it's going to be an inflection point, but our derivative is not 0. So let me write that a little bit clearer. It's going to be here. We don't stop, and we're going to hit this point, then keep going down to minus infinity. I'll try and make it look a bit smoother, just like that. And then when we come out of this portion, our derivative is going to be positive up until 4, it looks like, and then it's going to start decreasing after 4, and we're going to stay concave down the whole time. So we're going to go up, just like this. To hit this, we are concave down that whole time. We're going to stay concave down, but then our derivative is going to flip. So we're going to have a point there where we flip back down. We're going to keep going off and off, just like that. Oh, I got both of them. There we go. All right, and that looks just about right. Double check the derivatives. Those look right. Second derivatives also look right. And that is question 8. All right, for question 9, I just heard the AirPod. All right, let's finish this last question. For question 9, we want to write down the integral that represents the area of the region bounded by those 3 curves. So let's draw out a little axis here. We have y equals 1 minus x. So that's going to be kind of a curve just like this. We also have y equals 1. So they're going to intersect at the same point, right? And then lastly, we have ln of x. So that's going to go up through here. And so we know that ln of x, right, y equals ln of x, that is going to be equal to 0 when x is equal to 1, right? So we have the point 1, 0 right here. Let's see, when do these 2 points intersect? Well, y equals 1 is kind of going to tell you that. So we know it's x equals 0, y equals 1. Same thing for this term right here. The last one we have to figure out is when is ln x equal to y equals 1. Yeah, and so you can raise both sides to the e. We get e to the ln x, which is just x, is equal to e to the 1, which is just e. So x is equal to e, y is equal to 1. And so the way I'm going to do this is I'm just going to integrate it with x's. You could definitely do them with dy's if you know what that means, but why overcomplicate it? So the area is going to be equal to the integral. We're going to go from 0 to 1. And for this first portion, that's going to be up through here, drawing a line right here. That top portion is going to be y equals 1. The bottom portion is y equals 1 minus x, just like that, dx. And then we're going to add to that the integral from 1 to e. That's going to be this portion right here in orange. And that is going to be, the top is 1, and the bottom is going to be our ln x term, dx. And that's going to be our answer right there. No need to simplify. Actually, it doesn't say you don't need to simplify, it just says you don't need to compute. So this answer should be fine. I'll go ahead and simplify it a tiny bit from 0 to 1. 1 minus 1 is going to cancel. This just turns into x dx. And we're going to add to that the integral 1 to e of, you can't really simplify 1 minus ln x dx. That's going to be our answer right there. All right, next up, write down an integral that represents the volume of the solid obtained by revolving the region enclosed by those three curves about the line y equals minus 1. You do not need to compute the integral. So for this one, let's go ahead and draw it again. We have y equals x cubed plus 1. So we know our usual x cubed graph goes through the origin. We're adding 1 to that, so it's going to look something like this. Y equals 9. It's going to be somewhere up here. And x equals 0. That's just going to be this line right here. So this is going to be our region right here. Where do these points intersect now? So we know that this bottom point is just at 0, 1, right? This top point is going to be at 0, 9. And I'm just getting these from, the first one I got from when we plug in x equals 0, we just get y equals 1. And the second one, we know the line is at y equals 9. This point we're a bit more interested in, when is x cubed plus 1 equal to 9? Well, subtract 1 from both sides, we get x cubed is equal to 8, which gives us x is equal to 2. So you know that this is at 2, 9. So next up, we're revolving, don't forget, about the line y equals minus 1. So minus 1 down here, y equals. And so we're going to find the volume. We're going to integrate from, this is going to be from 0 to 2. Right? Those are the x values we're going between. And we're going to multiply by pi times the outer radius, which is going to be 9 minus the minus 1, right? This minus 1 comes from down here. So basically what we're doing is we're saying, okay, we want to take this area, and then we're adding that by subtracting, basically, because it's negative. And we're going to square that. And next up, what we have to do is we have to add to that pi times the inner radius squared, which is going to be our x cubed plus 1 minus a negative 1. Square that, and dx, right? It doesn't say much about simplifying, so I'll go ahead and simplify this just a bit. This is equal to the integral from 0 to 2. I'm going to factor out a pi here. And inside here, we get 10 squared, right? 9 minus minus 1 is 10. Plus, over here, we're going to get x cubed plus 1 minus this minus 1. Minus minus 1 is going to be 1. So we get x cubed plus 2 squared dx. And so this is just going to be equal to pi times the integral from 0 to 2 of, we'll just expand this 100 plus, it's going to be x to the 6th plus 4x cubed plus 4 dx, which is equal to pi times the integral from 0 to 2 of x to the 6th plus 4x cubed plus 104. That is not a 4. 104 dx. And that is our final answer. And that is the end of the exam. So nice job if you made it this far.